Okay, as we work through chapter 14, we want to pick up with the idea of turning an OH group into a good leaving group. So before we do that, let's just go back and review a little bit in terms of alcohols and alkoxides and also oxonium ions. So if I was to give you these terms, these alcohol, alkoxide, the alcohol, and the oxonium ion, and to talk about nucleophile, which one of these two molecules, the alkoxide or the alcohol, is the stronger nucleophile? That usually don't like to start off the quizzes within the first couple minutes, but let's go ahead and do that. So of alcohol or alkoxide, which one is the stronger nucleophile? Okay, if we look at this, the alcohol we classified as a weak nucleophile. Why? Because it was neutral. It's a neutral nucleophile. Alkoxide, we consider that to be a strong nucleophile. We also consider it to be a strong base as well. And we'll deal with that dichotomy, that sort of dual characteristic of an alkoxide. We'll continue to deal with that in the next, in this lecture video, as well as the next one as well. So now if I asked you which one of these two groups is a better leaving group, alcohol or oxonium ion, which one would you think? Go ahead, and when the answer pops up on this, or question pops up on the screen, which is a better leaving group, alcohol or oxonium ion? Okay, the OH group is a very poor leaving group, right? Why? Because remember, leaving group ability is based inversely on basicity. So this OH group, leaving is an OH minus. OH minus is a strong base, makes a poor leaving group. So what do we do to make the OH group leave? What did we talk about in the last lecture video? We protonate it to form basically a water molecule, and so the water molecule is a better or good leaving group. So what we want to do is we want to turn the OH group into a better leaving group, into a good leaving group, but we're going to have some issues that we have to overcome. So let's talk about how to do that, and then I'll show you how this will overcome one of the big issues that we have. So what we're going to do is we're going to turn an alcohol into what's called a tosylate ester. And so if I take just any kind of alcohol and I react it with what's called tosyl chloride. So I have a chlorine attached to a sulfur with two double bonded oxygens, and then I usually have a benzene ring on this side, and then usually I have a CH3 here. This is called para-toluene sulfonyl chloride is its actual name. And that's sometimes abbreviated then as tosyl chloride. Now, what will happen is, and we won't get too much into sulfur chemistry here, but I'll just go ahead and kind of show you what the mechanism of this would look like. Remember, the big difference in sulfur and carbon is sulfur can form an expanded octet because it's in row 3 or lower. So what would happen is the alcohol would actually come in and attack this sulfur, and then we take this pair of electrons and give it to that oxygen. Okay, if you're thinking, wait, I've seen that before, that's how we reacted carbonyls, right, with Grignards and with hydride. Only in this case, I'm doing it with an alcohol. So what I'm going to end up with then is I'm going to end up with the chloride attached to the sulfur. I'm going to have my 3 lone pairs on this oxygen with a negative charge. I'm going to end up with my sulfur attached to my benzene ring with the methyl group, and then I'm still going to have this double bonded oxygen, but now I'm going to have the alcohol, the whole alcohol molecule added here. And so what will actually happen then is I've still got 1, 2, 3, 4, 5, 6 bonds to sulfur. So sulfur has 12 valence electrons, sharing 12 valence electrons, which is perfectly fine. And so what will happen then is I'll bring this pair of electrons down. What's the best leaving group? The chloride is the best leaving group. So then chloride would leave, and you could think about making then the sulfur reestablishing its 2 double bonded oxygens. And then on this side I would have an O attached to my alcohol, but now I would have the hydrogen with the oxygen having the plus charge. And I should probably move that oxygen closer to the, or the plus charge closer to the oxygen. And then what happens? Then the next step is the chloride will come in, grab the hydrogen, and then this pair of electrons will go to the grab the hydrogen, the pair of electrons will go to the oxygen. And now what I will form is what is called a tosylate ester. Because now what I have is a sulfur double bonded to an oxygen, 2 oxygens with an OR group. So that's a sulfur ester. And it's called, this is the tosyl, this is called tosyl ester. This is called a tosyl ester. So what's the point of this? Well, the point of this is I can make tosylate esters. Tosylate, tosyl, people use different terms. Now, let's say I did this reaction and now what I had was a very specific one. So let's talk about this. Let's say I made this tosylate ester. And now what I have with this molecule is I have a really good leaving group. So that if I was to take even something like a chloride, the chloride could come in and attack the carbon, have the pair of electrons go to the oxygen, so that I would make my ethyl chloride, and then I would have my O minus with my S double bond O, and then my benzene ring. So a tosylate group is a really, really good leaving group. And why? Well, that if it's a good leaving group, it must mean that it's what? It's a very weak base. And sure enough, this tosyl anion is a very weak base. Why? Well, I will say it's a very weak base because it is very stable. And so if you think about the equilibrium that we had, where we said in previous lectures, we've said, well, if you take the acid and you dissociate it to form H plus and A minus, the way to shift this equilibrium to the right is to make the conjugate base more stable. Well, this is then stable. Its conjugate acid, which would be a sulfonic acid, would be very strong, but this would be very weak and also very stable. Now, why is this tosylate ion very stable? Because it has lots of resonance structures, right? I could take this pair of electrons, move it here, move that pair of electrons up there. So it's very stable because it has lots of resonance structures. Okay, so that's why it's a great leaving group, because it's a very weak base. Why is it a very weak base? Because it's very stable due to its resonance structures. So notice what I did here. By converting my alcohol into a tosylate ester, what I did was I can add nucleophiles and do SN2 reactions, because that's what this is. This is an SN2 reaction, and make that oxygen that was part of the OH is now part of the tosyl ester. And so now I can turn the OH into a very good leaving group. So tosylate esters, the importance of them is by using tosyl chloride, I can turn this OH group into a good leaving group. Now you might say, yeah, but what if you just turned the alcohol into reacted it with something like HBr and turned it into an alkyl bromide? Isn't the bromide now a good leaving group? And the answer is yes. And we'll talk a little bit about this, but we're going to need to turn the OH into a leaving group without the presence of acid. And here's an example of that. So let's say I wanted to do, basically, I'm going to put this in quotes. I want to do an SN2 reaction of an alkynyl anion with the alkyl group of an alcohol. And I would like to put that alkyl group, I would like to alkylate that alkynyl anion. Well, what would really happen if I did this reaction? If I took my alkynyl anion and I reacted it with an alcohol, what would happen? And this is an R prime, just meaning it's some alkyl group. What would happen is that C minus of the alkynyl anion would deprotonate the alcohol, and then the pair of electrons would go to the oxygen from the OH bond, and I would end up with the alkynyl anion becoming an alkyne, and I would make my alkoxide. And that's not what I want to do, right? What would I get? I would get an acid-base reaction. So, yes, I could turn this alcohol into an alkyl halide and do this SN2 reaction, but what I could also do is to say, well, if I want to do this reaction, let's turn this alcohol by reacting it with the tosyl chloride and make a tosylate ester. And so what I've done here is I've kind of shortened it up and said, oh, here's the specific, this R group, this is going to be that group. So I could turn my alcohol into a tosylate ester, and now what would happen? So for instance, let's say I reacted my alkynyl anion. I wanted to take my alkynyl anion and I wanted to convert it to this basically this is a but1-ine. Well, and all I had lying around was some ethyl alcohol. What I would need to do is to take that ethyl alcohol and react it with the tosyl chloride. And what would that form? That would form my tosylate ester. And now I could react my alkynyl anion and have it come in and do an SN2 reaction and now kick off the tosylate group as the leaving group, and I would end up now alkylating the ethyl group, and I would make my leaving group the tosyl anion. So I could do this SN2 reaction using the tosylate ester. And so it's giving me the idea of turning this OH group into a good leaving group. And doing it in a way that I never had to react this with acid. Okay. And we'll talk about converting this OH group into a halogen because that's another approach that I could use. So then, just to complete this, what I already wrote was that the nucleophile would come in, do an SN2 reaction, and I would get the excellent leaving group of the tosylate. Now, this reaction right here I want to talk about on the next slide, and I want to propose a problem to you. And that's this. Let's say I had this alcohol, and I wanted to form, out of that alcohol, I wanted to form this alkene as the major product. What reagent should I use? Well, how about H2SO4 and heat? Let's do dehydration. How would that mechanism work? Well, never a bad thing to review mechanisms. So let's take the alcohol. Let's protonate it from sulfuric acid. And let's form the oxonium ion. And then I would also have my HSO4 minus. And if you're kind of going, doesn't that look an awful lot like a sulfonate? It does, because that's the standard sulfur chemistry. So now when I form this oxonium ion, what happens next? Well, since this is a secondary system, the water's going to leave. And I should be putting equilibrium arrows here because all of these are reversible steps. And now I'm going to end up with my carbocation and my water. And then what happens to form this alkene product? Well, you could think the HSO4 minus or the water, and actually in this case let's draw this correctly. The correct way of doing this. The correct way of doing this would be to bring the water in and have the water grab the hydrogen. It doesn't grab it, remember, the H plus kind of falls away and the water catches it. So that then what I would do is then I would end up forming the double bond. Now, why did I form the double bond here? And then, of course, I'd end up with H3O+. Why did I end up forming this double bond? Because that double bond is the most substituted, which means I just formed my most stable product. What mechanism is this overall? Well, since it involves a carbocation, the overall mechanism here would be considered E1. Right? I'm forming a double bond. It's elimination through a carbocation intermediate. It's E1. So I'm going to form the most substituted double bond. Okay? That's great. But just going to check and see if I had another blank slide. I don't want to form the most substituted product. I want to form the least substituted product from this alcohol. What reagent should I use for that? Well, here's a trap that I set for people that they could fall into. You would say, I want to form the least substituted double bond. First of all, hopefully you remember that that means I would use terse butoxide, right? And would that be the product that I get if I reacted this alcohol with terse butoxide? The answer is no, that's not the product I would get. What would I get? Well, the tertiary butoxide would sort of deprotonate the alcohol, and I would end up with an equilibrium between the alkoxide of the cyclohexane alcohol and the alkoxide of terse butoxide. I would end up with an equilibrium, right? Because I'm basically an alkoxide deprotonating another alkoxide, that's an equilibrium reaction. I wouldn't do E2 because how do I do E2? It's not a OH group that's present here, it's a halogen. So if I reacted the halogen with terse butoxide, there's my alpha carbon, here are my two beta carbons. Remember that the terse butoxide always does an E2 elimination. So I locate my alpha and my beta carbons, and then my beta hydrogens. Can these beta hydrogens become antiperiplanar to the halogen? Sure, because they're not a cis trans. There's not locked into cis trans by a ring. So both of these beta hydrogens can be removed. Which one will be removed? The one is least sterically hindered, which is the one on the right. So my terse butoxide would come in, grab that hydrogen, and we would do an E2 elimination so that I could form the double bond to the least substituted double bond, the so-called Hoffman product. But it wasn't an alcohol that I did this with. It was a halogen. So you might say, okay, well, if I want to convert this alcohol into the least substituted double bond, then just do this. Just go ahead and convert this alcohol into a halogen. And how would I do that? Just react it with HCl, HBr, HX. And that would turn that alcohol into this halogen. Then react the halogen with terse butoxide. And I could get my least substituted double bond. You also might now at this point say, well, I see the point of the tosyl chloride. So now what I could do is I could just say, you know what? Let's take this alcohol, let's react it with tosyl chloride. So that I can convert that alcohol into a tosylate ester. Okay. Now I'm running out of space. I'll just kind of squeeze out the... And now what do I have? Now I've got a leaving group just like this halogen. So if I want to make this product, what do I do? Now I can just treat this with terse butoxide, and it will remove the least substituted hydrogen. So now I've got more than one way to do an E2 elimination. I could convert the alcohol, the OH group, into a tosylate ester, and then do E2 on it. I could also just convert the OH group into a halogen. But the critical part here is that terse butoxide can only be used with a halogen or with the Tosylate ester. Okay, so this is the usefulness of turning OH into a good leaving group, is the fact that now once I turn this OH group into a tosyl group, tosylate ester, I could do substitution, I could do elimination. And most of the time, if I'm just looking to form the most substituted double bond, I can just do that with sulfuric acid and heat. I can just do standard dehydration. But if I want the least substituted double bond, well, then I have to either turn the OH group into a halogen or turn it into a tosylate ester, because that's the only types of molecules that are going to react with a tertiary butoxide. So that's one of the importance of tosylate esters in terms of being able to give us options, in terms of being able to do SN2 reactions and also E2 reactions. Okay, so this just shows that SN2 reaction again. Okay, so that's the use of tosylate esters, and we'll come back to those in a couple of minutes. You can also basically use tosylate esters to do reductions of alcohols. Now, reduction again means loss of oxygen, gain of hydrogen. So if I wanted to remove this OH group and turn this cyclopentanol into cyclopentane, how would I do it? And one way would be to use the reactions we already know and say, well, let's go ahead and use acid and heat. Where did that acid come from? It came from sulfuric acid, so let's do dehydration. With sulfuric acid and heat, turn this into a carbon-carbon double bond, and then use our hydrogen and palladium or platinum to hydrogenate the double bond down to an alkane. So I could do that. If I wanted to reduce, if I wanted to remove an OH group, or better yet, substitute an OH group with an H. But you could think about doing that with a tosyl chloride as well. React the cyclohexanol in this case with tosyl chloride and make this tosylate ester. And then use H-. The H- would come from either sodium borohydride or lithium aluminum hydride. And that H- could now do an SN2 reaction by coming in and kicking off the tosyl anion. And so I could do an SN2 reaction in essence to reduce the OH group down to an H. So again, another use of tosyl chloride, but basically this mechanism is just simply nothing more than an SN2 mechanism. Okay. Now, we know, for instance, that we can convert the OH group into a halogen by reacting it with either HCl or HBr. We saw that in the first semester course. And so what would happen? What would happen is, and I'll fill in some of the blanks here, if we take our alcohol and react it with something like HCl, the O is going to bond the H+, the pair of electrons will go to the chlorine, and I'll form an oxonium ion. And then if this is a secondary or if this is a tertiary alcohol, the water will leave to form a carbocation. And then that carbocation, the halogen will come in and add to it to form the final alkyl halide product. So in this case, this would be a Cl-, and it would form an alkyl chloride in this case. Now remember that when we react a primary alcohol under that same set of conditions, what happens? The OH group gets protonated, we form the Cl-, and we form the oxonium ion. But now what we're going to do is we're going to do an SN2 mechanism on the reaction to form this. And this, I'm going to put a big X through that, because if you ever wrote an SN2 reaction with that mechanism, that's what you got, was a big X and 0 points through it. Let's write let's write out what it should really look like. Right, our chloride in this case would come in, do backside attack, and then the water would leave. The transition state would look like this. Right, that would be our transition state. And then it will go to form the final product, which is going to be, in this case, it's going to be that product. So in terms of the charges in the transition state, chlorine is going from -1 to here 0, so it's delta minus. The oxygen's going from +1, and the final product here would have water, so it's delta plus. So that would be the way to truly write that mechanism, not this kind of crap, because that doesn't get you any points. So writing this structure. Okay. So we know how to substitute the OH with a halogen. But there are some issues. And the limitations on reacting an alcohol with something like HCl or HBr to form the alkyl halide, the limitations are that HI just doesn't react. So this is not a good way to put an iodine to make an alkyl iodide. The primary and secondary alcohols do require heat to make this reaction to go. We used to do an experiment in the first semester, which we didn't do this summer, but we have done in the past, where we basically try and take butyl alcohol and react it with sulfuric acid and sodium bromide to make butyl bromide. And that experiment is going to be modified in the future, but what would happen is the sulfuric acid would protonate the OH group and it would form an oxonium ion, and then the bromine would come in and do SN2 on that. And this would take a 45-minute reflux, meaning that we basically would boil the solution for 45 minutes to get this reaction to go. And it required concentrated acid. It was just a mess. It wasn't even a hot mess. Well, it was a hot mess because you were refluxing it for 45 minutes, but it was a mess. We had to use concentrated sulfuric acid. People would get one year a sleeve of a sweater dissolved. Jeans got holes in them. Oh, it was just a nightmare. So that experiment's gone in the future. But the point is that if you're going to react a primary or secondary alcohol with HX, it requires heat. And that heat will also cause an E2 reaction to occur, so that we could end up, once we form this oxonium ion, does the nucleophile come in and do SN2, or do we lose a beta hydrogen to get an E2? So we get actually both products. And of course, what I didn't say about the last problem was that if we were reacting this with HCl, and we formed as part of that this carbocation, would it also not be possible for this hydrogen to shift, to do a 1,2 hydride shift to form this more stable tertiary carbocation, and then that's where the Cl- would add. So another disadvantage here is that it can lead to carbocation rearrangements to give us the product that we really don't want. So for the most part, if you have a tertiary alcohol and you react it with HCl or HBr, that's perfectly fine. That reaction goes really, really smoothly. It's the secondary and primaries that are a bit of a problem. So here is, another example. Let's say I wanted to convert this basically this is a neopentyl alcohol to form neopentyl bromide. If I tried to react this with HBr, it would not form that product. And let me just kind of think about that and show you, as again, review. It's always good to review what I would be looking for. And so the oxygen would be protonated by the H, the pair of electrons would go to the Br. And so what would I end up forming? Well, in this case, I would end up forming the oxonium ion. Now, what I just described with this primary system is that the Br minus, if you heated this, the Br minus would want to come in and do SN2, except what's the problem? The problem is it's got this big basically what is in essence a tertiary group in the way. And so this reaction will not go. That's too sterically hindered. And so what would happen most likely in this case was if we heated it up, one of the methyl groups would shift over and we would do a 1,2 methyl shift to then give us the methyl shifting and the water leaving all at once to then give us this tertiary carbocation, which then the Br minus would come in and add to. So either we're going to get no reaction or we're going to get a rearranged product. So that doesn't work all that well. So are there alternatives to using something like HBr, HCl? And the answer is yes. Here's another example. Maybe I'll make this one of the online quiz mechanism problems for you to write the product of this where this molecule undergoes a hydride shift. So what are the alternatives to adding HX to an alcohol? Well, one of them is to react a phosphorus halide. And it could be PCl3, it could be PCl5, it could be PBr3, phosphorus trichloride, phosphorus pentachloride, or phosphorus tribromide. If you react those reagents with an alcohol, they will form the alkyl halide, either the alkyl chloride or the alkyl bromide. And the advantage of using these phosphorus halides is that they react much easier with primary and secondary alcohols, and they do not undergo carbocation rearrangements. So the sole purpose of these reagents for the moment is that they replace an OH group with the halogen. So they're good alternatives for forming alkyl halides from alcohols. Now, there are some stereochemical consequences to reacting chiral alcohols. So let me talk a little bit about those. And I'll just show you the mechanisms because I wrote these out last fall or last spring when people were asking about them. So, and these are from the Top Hat textbook. So if I was to react a chiral alcohol with HCl, what would be the product that I get? Would it be optically active or would it be a racemic mixture? And we can answer the question to that relatively straightforwardly. I would take the OH group and I would react it with the H+. Now again, remember the way we've been drawing mechanisms, I would break the HCl bond and give that pair of electrons to the chlorine. And then I would form this oxonium ion, which since it was attached to a secondary carbon, I would then break the carbon-oxygen bond to form water and then my carbocation. Now remember, a carbocation is sp2 hybridized, and as it being sp2 hybridized, it has my empty p orbital. And so when the chloride comes in and adds, it could add 50% from the top, 50% from the bottom. And so what would happen? I would get a 50-50 mixture of the two enantiomers. So I would get a racemic mixture. So that's characteristic of any carbocation mechanism. It always gives us a racemic mixture. So if you reacted a chiral alcohol with HCl, you would make a racemic mixture of the alkyl halide. Now, there's another reagent that you can use that will replace an OH group with a chloride, and it is to do basically the reaction with the tosyl chloride and then use Cl minus. So in other words, do this reaction SN2. So what will happen is, in this case, is that if I react the alcohol with tosyl chloride, what did I not end up doing? I end up forming the tosylate ester as we saw earlier. Now the chloride can come in and do backside attack on the tosylate ester and kick off the leaving group, so that now what I'd make is now I can make the inverted product. So if I started over here with group number 4 is away, so this is 1, 2, and 3 clockwise. So if I started with the R, I would end up with the S with 100% inversion of configuration. So we can use our tosylate esters to convert the OH into a Cl, but the stereochemical consequence of this is we would end up with 100% inversion. I'll modify that in a coming slide, because this is a fairly controversial topic as to whether it goes by inversion or retention. Now PBr3 actually ends up with inversion of configuration. So this is the mechanism from the Top Hat textbook. What happens is the OH group of the alcohol will come in and attack the phosphorus and kick off a bromine. And so when that happens, it basically forms the oxonium ion, and now the phosphorus has 2 bromines attached to it. So then what will happen in this case is that bromine I just kicked off in this process is now going to do backside attack and kick off now this entire group, which will basically make the oxygen, which would normally be a water molecule, right? It would normally be an oxonium ion that way. It now ends up forming an OH to phosphorus bond. And so if you react PBr3 with a chiral alcohol, you end up with, again, 100% inversion of configuration because of this mechanism. It basically, the alcohol reacts to form this species, and then the bromine that was kicked off of the phosphorus does a backside attack, so that we end up with an SN2 mechanism. Okay. Now, the SO2Cl is a new reagent that we can use to replace an OH group with a chloride. So SOCl2 is called thionyl chloride. And thionyl chloride, depending on the textbook that you look at, will either go by inversion of configuration or retention of configuration. And it turns out it depends on the solvent that you use. So this, with pyridine, it gives inversion of configuration, and then with an aprotic solvent like ether, it gives retention of configuration. And so Top Hat is really good about explaining why there's this discrepancy in the internet and in textbooks as to whether SOCl2 undergoes an inversion or retention. So here's the mechanism that they show, and I'm just going to step you through it. This isn't a mechanism I would ask you to do. But SOCl2 has an S with 2 Cl single bonds, a double bond to the oxygen, and this lone pair. So the OH group attacks the sulfur and the pair of electrons goes to the oxygen and then forms this O- species. Well, the O- species would like to reform the sulfur-oxygen double bond, and so it brings its pair of electrons back down. What's the better leaving group? One of the chlorines. So basically what we end up doing is we end up losing a Cl-. Then, in the presence of pyridine, so we'll talk more about this as an aromatic, heterocyclic aromatic compound, but pyridine, for this purpose, is a base, with the nitrogen having a lone pair being a fairly strong base. And so what happens is that once the pair of electrons comes back down and we kick off the chlorine, we still have this OH plus, and the pyridine comes in as a base and it removes the H plus so that this pair of electrons can now go to the oxygen, and I can basically now form my oxygen species that's now attached to an S with a double bond with a Cl on the other side. Well, if you have pyridine present, there's more pyridine around, so now the pyridine acts as a nucleophile with its lone pairs on the nitrogen, adds to the sulfur, and that pair of electrons moves up there. So now what I form is an O- species with an N+. The sulfur still wants to reform the SO double bond, so it brings this pair of electrons back down. What's the better leaving group? Chloride. And so now we end up with this species where the nitrogen of the pyridine has a positive charge. So the chlorine that just got lost, the chloride that just got lost, is now going to come in and it's going to do a backside attack on this carbon, causing this to basically break apart. So there's not this whole thing will leave, but it's breaking apart as it's leaving. So the Cl- comes in, attacks this carbon, the CO bond breaks, and the pair of electrons now goes to the sulfur to form an SO double bond. And at the same time this pair of electrons moves to form the SO double bond, this sulfur-nitrogen bond breaks to give the pair of electrons back to the pyridine. So what I end up doing is getting my inverted product, forming two SO double bonds, which this is sulfur dioxide, and then the pyridine gets back its pair of electrons, so it goes back into being intact. And so in the presence of pyridine, SOCl2 will do inversion of configuration. It will give you the opposite chiral center. In an aprotic solvent where the pyridine isn't present, the mechanism goes a little bit differently. So we still have the OH group attacking the sulfur and the pair of electrons going to the oxygen to form this SO- species. Then this SO- species, the pair of electrons comes back down to reform the SO double bond and kick the chlorine off. And so it ends up forming then this species that we saw before. Now the Cl- can come in and grab this hydrogen and have this pair of electrons go back to the oxygen so that I can form this species. Okay. So this chlorine removed this H plus and left that oxygen now neutral. So then what happens is, and the Top Hat book has a much more detailed explanation of this, what happens is that basically the chloride that's attached to the sulfur will attack from the same face, and the pair of electrons will go to the carbon-oxygen bond will break, and that pair of electrons will go to form an SO double bond. And so we end up with basically a retention of configuration. So if you think of it this way, the oxygen is here, the sulfur is here, the chlorine is here, and so there's a lone pair here. So what happens is we take this pair of electrons, and let me just write in. Right, so there's my carbon with my 3 groups. I'm going to break the sulfur-chlorine bond and have that pair of electrons go to form the chlorine-carbon bond. Then take this pair of electrons and use it to form the SO double bond. So that in the end I end up with SO2 and I end up with a retention of configuration for that alkyl halide. So this is the reason why there's 2 different mechanisms that are often proposed. Okay. So that's sulfur chemistry, phosphorus chemistry are a little bit different than carbon. Okay. So that's the reactions of chiral alcohols. They can go by, just to review, if you react a chiral alcohol with just HCl, you're going to get a racemic mixture. If you react it with tosyl chloride followed by the halide ion, you're going to get 100% inversion because it's going to do an SN2 mechanism. If you react it with PBr3, you're also going to end up with 100% inversion of configuration because you're basically going to change that oxygen into a good leaving group when it adds to the phosphorus, and then the bromine is going to end up adding from the backside. And for SOCl2, thionyl chloride, you can end up with either inversion of configuration if you use pyridine, or you can end up with retention of configuration if you just use an aprotic non-hydroxylic solvent and not pyridine. Okay, so there's all of these different ways to make the OH group leave, and a lot of different ways when dealing with a chiral alcohol to preserve its stereochemistry or to invert it. Okay. Now, dehydration of alcohols, we've talked about. I'll just give you, this idea that we did this reaction. We said if we reacted this with H2SO4 and heat, what did I end up doing? I end up dehydrating to form the most substituted double bond and water. Okay, and you could draw the mechanism of that reaction out. I think we actually already did. So that's how we can dehydrate alcohols, and that's just simply nothing more than a review that we had done before. I will just take a minute here. Well, it'll be more than a minute, but if we reacted this with H2SO4, and I'm going to go ahead and react this alcohol, this primary alcohol, with H2SO4. A pair of electrons would be used to bond the H plus, then the pair of electrons going to the oxygen. So now what I end up doing is forming my oxonium ion, and then the HSO4 minus ion. Then if I heat this, what will happen is, here's my alpha carbon. In this case, there's only one beta carbon and only one beta hydrogen. So in the presence of heat, what would happen is, and also in the presence of heat, but the absence of a really good nucleophile, the pair of electrons will move that. I'll lose the H plus and kick the water out at the same time. And remember, the HSO4 is just going to catch the H plus as it leaves. And so I would end up then forming my double bond, in this case, plus water plus my H2SO4 catalyst. So this overall mechanism would be classified as an E2 mechanism because it did not undergo a carbocation intermediate. You could also have this reaction undergo some sort of hydride shift that would produce a secondary carbocation, and that secondary carbocation then would form the most substituted double bond. So we talked about dehydration reactions last semester, and so this is just kind of reviewing that topic. But it is another reaction of alcohols, which is kind of where we're at right now. We're at the reactions of alcohols. Okay. So those are the reactions, syntheses of alcohol. So the next functional group that we're going to talk about are ethers. So an ether has two alkyl groups attached to the oxygen. And they don't have to be the same alkyl group. One could be a methyl, one could be an ethyl. There's lots of different ethers out there. The ones that we use in the lab most often are diethyl ether, or I guess the di is redundant. So if you could also call this just ethyl ether. And I'll talk about the reactions of ethers. There really aren't very many, and so they're usually used as solvents or fuels. Another ether that's commonly used is tertiary butyl methyl ether, which is called TBME. Sometimes called B-Tex, I believe. Tertiary butyl methyl ether is one of the additives, one of the oxygenates that they add in gasoline, particularly in the winter climate areas, to reduce the amount of carbon emissions that you get. And also, I think it probably has some effect on a little bit of the ozone type reactions as well. But TBME, or tertiary butyl methyl ether, is one of those compounds that they do add to gas as oxygenates. They can just add ethyl ether as well. They can just add ethanol to the gasoline as an oxygenate, but they also add TBME. And TBME is a tad bit maybe carcinogenic. So there were lots of problems if the gasoline tanks at the gas stations leaked into the soil, because this compound would then leach into the soil with the gasoline. So it still is used, but it's not particularly great. And it can be an environmental problem. Diethyl ether we use in the lab because it has a very low boiling point. It has a low boiling point of about somewhere in the 35-degree range Celsius, so it's very low boiling point, but it's also exceptionally flammable and has no problems in catching on fire with a spark. Its vapors are heavier than air, so that it could travel if you had a bench top and one person was working with ether down here. The vapors could travel up the bench top until they hit a flame, and then boom, then we have a fire. And for those of you who were in the lab course during the summer, we talked about ethers in a couple of problem areas, which we'll talk about here in terms of their flammability and also their ability to make peroxides, and we'll talk about that in a minute as well. So ethers really they have two reactions that they can undergo. So the two reactions of ethers are, number one, combustion, which we avoid at all costs when we use diethyl ether in the lab. But number two, they can undergo a cleavage reaction, and we'll talk about that. And then I guess a third reaction that is unwanted is they can form peroxides, organic peroxides, and that also leads to explosions. So we'll talk about those three reactions. The main use of ether then, since these reactions are somewhat hard to occur, the main use of ethers is as solvents, because they really don't react all that well, except burning and except forming peroxides, both of which we can control. So that's what we can do. So in terms of syntheses of ethers, how can we do that? And let's talk about the traditional way to make ethers. The traditional way is to use what's called the Williamson ether synthesis. So Williamson ether synthesis. The Williamson ether synthesis starts by taking an alcohol and converting it into an alkoxide, and then reacting that alkoxide with a halide in an SN2 mechanism to then form the ether. So that's the overall way to do Williamson ether synthesis. Traditionally, the alkoxide was formed by using either sodium metal or potassium metal. And the restriction on this alkoxide reacting with the halide is that the halide either has to be primary or secondary. And the textbook would have a problem with the secondary, but as long as this is a small alkoxide, we could go ahead and use a secondary halide to form the ether. So Williamson ether synthesis is basically using an SN2 type of a approach. Now you could say, well, can I use anything but sodium or potassium to make the alkoxides? Hey, whatever method you use, whatever you want to use. So you could use a C minus, you could use an N minus, you could use an H minus, right, to make the alkoxide. So you could either deprotonate or use sodium or potassium metal. Traditionally, Williamson ether synthesis has used the metals. So in the Williamson ether synthesis then, what happens is this. Let's take a very specific example. Let's say I take my ethanol and I react it with sodium metal so that I'm going to form my alkoxide, which is going to be small, right? This is a small alkoxide, not sterically hindered. And I'm going to react that with, let's say, propyl chloride, a primary halide. And so what's going to happen? The O minus is going to come in, attack the carbon, kick off the leaving group, and what am I going to end up making? I'm going to end up having an ethyl group on one side and a propyl group on the other, and then end up with a Cl minus. Okay. And in terms of the transition states, since this is an SN2 mechanism, always good to review our transition states. What would our transition state look like? It would have the oxygen partially bonded to the carbon, with the leaving group being the chlorine, and then this carbon is the one attached to the chlorine. It's got two H's and it's got an ethyl group attached to it. And it doesn't matter where those groups go in relationship to the bold wedge, the dashed wedge, or the bond in the plane, because this isn't a chiral center. In this case, in this transition state, the oxygen is going from -1 to 0, so it's delta minus. The chlorine's on its way from 0 to -1, so it would be delta minus as well. Okay. So we're going to say that you can react small alkoxides with primary or secondary halides and do Williamson ether synthesis. Do the SN2 reaction to give you the ether. Okay? And that's going to be an oversimplification, but I can live with that. And hopefully you can too. But what would happen if I tried this reaction? If I tried to actually react the alkoxide with a tertiary halide, what would I get? Now, just as a point of reference, from last semester, remember that we did this reaction. We took our alkynyl anion and we tried to alkylate it with tertiary halides. And what happened? Well, in both of these cases, what do we have? We have strong nucleophiles that are also strong bases. And so they have this kind of dual reactivity. And so back in that case, when I talked about alkynyl anions, and now we're going to apply this to small unhindered alkoxides, when they have this dual characteristic of being a strong nucleophile or a strong base, their primary characteristic, their first, I'm going to give them human characteristics, their first instinct is to be a strong nucleophile. And so they'll try and do SN2. And if they are rebuffed, if they can't do SN2, they'll turn around and act as a strong base and do E2. Okay, that's essentially the way that these strong nucleophiles that are also strong bases react. Their first instinct is to try and do SN2, and if they can't, I usually say they usually get angry and then they rip off a beta hydrogen to do E2. Again, giving them human characteristics. So this alkoxide trying to react with a tertiary halide, can it do SN2? No. Right? This can't do SN2 because it's a tertiary halide. It's too sterically hindered. So what's it going to do? It's going to act as a base and do an E2 reaction. So what's going to happen? Well, here's my alpha carbon. Here's a beta carbon. Here's a beta carbon. Here's a beta carbon. And so I'm going to rewrite this. So I'm going to have the beta hydrogen. This carbon would have the same beta hydrogen, right? And so alpha, beta, beta, beta. So I have these two beta hydrogens, and there would be another beta hydrogen, or there is another beta hydrogen down here. Let me erase that. CH3 and make it a CH2 with an H. So there's 3 beta hydrogens, but if I called this beta hydrogen A, that would be A, and that would be B, so that these two would give the same product. So this reaction is going to go by E2, because as a tertiary halide, this cannot undergo SN2. It's only going to undergo E2. So then the question becomes, which beta hydrogen is it going to deprotonate? Is it going to deprotonate HA, or is it going to deprotonate HB? So my question is, which one is it going to deprotonate? What's the major product of the reaction going to be? So why don't you give me your thoughts on that when the video stops? Give me an answer, and then we'll come back and take a look at it. Okay, so let's write the product. So if the alkoxide comes in and grabs HA, pair of electrons moves, chlorine leaves. So the product of losing HA is to form this product. And the product, if I was to have the CH3O- react with HB, have that pair of electrons move, not there. But have this pair of electrons move here, then kick the chlorine off. Now what I'm going to end up with is the double bond to the CH with the CH3 there. And that would be product B. So which one of these two products is going to be the major product? Well, that's going to depend on how we view this as a base. Is it a sterically hindered base, or it is a small unhindered base? And the way I characterize it as a small unhindered base. So if this is a small unhindered base, it's going to be like our NH2- that we used last semester. And so therefore, it's going to be able to equally get at HA and HB. Well, which one is it going to deprotonate the most? It's going to form the most stable alkene, the most stable product, which again is the most substituted alkene. So B would be the major product of this reaction. Okay, so the alkoxides with a tertiary halide react very similarly to when the alkynyl anions reacted with a tertiary. And we're going to hold on to this idea that when you have nucleophiles that are also strong bases, their first instinct is to do substitution, and if they can't, they're going to do E2. And then the question is it a hindered or unhindered base? So Williamson ether synthesis can be done, I'm going to say, with primary and secondary halides. But once you get to a tertiary halide that's hindered, it's going to do E2. So that's a limitation on the Williamson ether synthesis. Okay. So that's one of the ways to make ethers. Well, we can also make special ethers called epoxides. And I should say epoxides, a review. Right? Because we've done this reaction before. So if I take my carbon-carbon double bond, and I want to convert that into the epoxide with I'm kind of looking at it on its side now. What reagent would I use for that? I have two choices. My first is to use a peroxy acid, something like MCPBA that I told you about last semester, but we'll just say a generic peroxy acid. We'll plop the oxygen right down, bond that oxygen to both carbons at the same time, so that I'll end up with this epoxide. What's the other way to do this reaction? The other way is to react the alkene with Br2. Right, so I'm going to add 2 Brs to the double bond. 100% trans, although in this case it doesn't really matter. And will that get me anywhere? It will not, because I don't want a second bromine here. Right? What do I want here? I want to react this with Br2 and water. And so I should erase this bromine as well. So I'm going to react this with bromine and water. So I'm going to add a Br and an OH. The Br added here. The OH adds to the carbon with the most substituents. Now, I then am going to treat this with hydroxide. And what's going to happen, the hydroxide is going to deprotonate the OH. And I'm going to make this alkoxide. And that alkoxide is now going to do what? It's going to do an intramolecular, meaning within the same molecule, an intramolecular SN2. So the O- is going to react with carbon, kick the bromine off, and what do I end up making? The epoxide plus a Br-. So that's the second way to make an epoxide, is by making the bromohydrin and then deprotonating it to form the epoxide. So that's how we can synthesize epoxides, and that's a review from last semester, but again, it's always good to review. Now, let's do reactions of epoxides. Another review. So when I have my epoxide here, and this is a review from the last problem set that I gave you from the last class. So it's a really current review. But if I was to react this epoxide with acid and, let's say, chloride, what would my final product be? And then if I was to react this, so this is acidic. That's going to be opening up the epoxide under acidic conditions. What happens? What happens is I protonate the oxygen. If this is a bond, then a pair of electrons goes to the carbon. I form the oxonium ion. And what happens with that positive charge? It distributes a lot of that positive charge down to the carbons. Now my Cl- is going to add to which carbon? Because I did this with acidic, the nucleophile adds to the most substituted carbon of the epoxide. And so the chloride's going to add here, and then the OH will swing over. Remember, this is always 100% trans. The nucleophile and the OH group will always be 100% trans. And so what am I going to form? I'm going to have my chlorine added here, my two methyl groups here, my OH group now here, and then there were two hydrogens there. So the nucleophile under acidic conditions always adds to the most substituted double bond. What if I took this Grignard, or what if I took this and reacted it with a Grignard? What if I reacted it with something like CH3 minus MgBr plus? What's going to happen? Well, this is what I call strong nucleophile ring opening. And what's the CH3 minus going to do? The CH3 minus group is now going to attack the carbon that is least substituted. And then the oxygen's going to swing over to the left. So when you use strong nucleophile, what happens? The nucleophile adds to the least hindered carbon. And so in that case, again, it would be 100% trans addition relative to the OH group. So now I'm going to end up with my O minus swinging over to the most substituted carbon, and my CH3 group now adding to the least one. And then what happens, well, whenever I use an anion, I then have to have a then H plus H2O step to protonate then the O minus to form then the final product. So again, when opening up epoxides under acidic conditions, the nucleophile adds to the most substituted carbon. Under strong nucleophile conditions, or what the textbook sometimes called basic conditions, what does the nucleophile do? It adds to the least hindered carbon of the epoxide. So that's our reactions of ethers. Okay, so that was just a quick review because we talked about that a little bit in the last lecture video. So in the next video in this series, we're now going to talk about more reactions of ethers, but not the epoxides, more or less the traditional reactions. We're also going to talk about how to prepare ethers, one more review reaction, and then we'll talk about some new reactions to make ethers and new reactions